Objectives for today. Name and describe the 3 methods of thermal energy transfer. So today we're going to talk about 3 different ways energy is transferred from object to object, specifically thermal energy. Then you will need to be able to give me the names of those 3 types and give a rough description of each of them. 2, describe the characteristics of conductors and insulators. So we're going to talk more in depth about conductors and insulators. We talked about them in the lab yesterday, but we're going to describe them so you will be able to identify if something is a conductor or an insulator. Then, identify what happens to objects that causes thermal expansion and contraction. So we're going to talk about thermal expansion and thermal contraction, and you will need to be able to describe not only what that is, but what causes it. And then the last objective is to be able to explain how convection currents form. So we're going to talk about what a convection current is, and you're going to describe the steps for that to form. Thermal energy is transferred in 3 different ways. The first way we're going to talk about is radiation. Radiation is the transfer of thermal energy from one material to another by electromagnetic waves. You know what electromagnetic waves are. We've discussed them already. We learned about the whole electromagnetic spectrum, which included light. So those waves are transferring thermal energy. All objects are able to transfer thermal energy by radiation. So you are able to do this, your desk is able to do this, a campfire is able to do this, but objects that are warmer are able to emit more radiation than cold objects, which is why you will be more likely to be able to feel the radiation off of a campfire by holding your hand up than you are to feel it off of an ice cube. Question?
Is this like the same radiation that they use for cancer?
No. This is a different type of radiation. When we talk about radiation that they use to treat cancer, they're using radioactive elements, and so elements are decaying, and that's a different type of radiation.
Is this like radiation from nuclear stuff? Like the same stuff?
So the nuclear radiation stuff has to do with the same type of radiation from cancer. So it's different.
Sorry.
Good questions, though. So if you hold your hand above a campfire, you will feel the heat radiate off of it. Okay, you won't actually have to be in contact with the flames in order to feel the heat, because like light, radiation of thermal energy does not require matter to travel. It can still travel through solids and liquids and gases, but it doesn't need them to be there, which is how that radiation gets to us from the sun. Conduction is the next type of thermal energy transfer. This is the transfer of thermal energy between materials by the collision of particles. This requires the materials that energy is passing between to actually be in physical contact with each other. Because in order for my hand to transfer energy by conduction to this tabletop, the particles from my hand have to actually collide with the particles from the tabletop. When a high energy particle from a substance that is warm runs into a low energy particle, then it's going to transfer some of its thermal energy to that particle. Like heat, this moves high to low. So you're never going to have a warm particle with lots of energy run into a cold particle with very little energy and take the rest of that particle's energy. It's always going to go high energy particle gives energy to low energy particle. That's the way energy moves, from high to low. For example, water vapor that's in the air is in a gas state, which means that it has a lot more thermal energy than the cold glass sitting on your tabletop in the summer. And what happens is if a molecule of water that's in the air runs into the side of that glass, it's going to transfer some of the energy from that particle to the glass. And as a result, when it loses energy, it will lack the energy to stay in a gas form, and it will become liquid water and condense onto the side of the cup. That's how you get condensation on your glass in the summer. Some materials pass energy by conduction better than others. A thermal conductor is a material through which thermal energy flows easily. Metals are good conductors, and they are good conductors because metals have electrons that move easily. They move around the atoms of those substances very easily. Because when I touch a surface, what is actually happening is the electrons on the exterior of my atoms are touching the electrons on the exterior of the atoms of that surface. So when we say that atoms are touching or colliding, what's actually happening is their electrons are colliding. So if you have electrons that move very easily, like a metal does, then they are more likely to come into contact with the electrons of the surface, and therefore more likely to pass that energy on easily. Whereas thermal insulators are made of materials where those electrons are not easy to move, and therefore they're way less likely to come into contact with electrons of another surface and pass on any energy. Non-metals tend to be insulators because they tend to have these characteristics for their electrons. Some materials are easier to heat than others. Specific heat is a description that we use, or a measurement that we use to describe how easy it is to heat something up. If something, the specific heat of something is how much energy is required to increase the temperature of that material, specifically 1 kilogram of that material, by 1 degree Celsius. So if you had a kilogram of gold and you measured how much energy you put into it until it reached 1 degree Celsius higher than where you started, you would know the specific heat of that chunk of gold. Every material has its own specific heat. So gold has a specific heat, water has a specific heat. Different metals have different specific heats. Different plastics have different specific heats. So all materials have their own. It takes less energy to raise the temperature of a material that has a low specific heat. So if we go back to that agree-disagree statement, they said that it would take a lot of energy to raise the temperature of a material with a low specific heat. So we would actually disagree with that statement. It does not take a lot of energy to raise the temperature of a material with a low specific heat. Conductors tend to have lower specific heats than insulators, so it tends to not require as much energy to raise the temperature of a conductor as it does the temperature of an insulator. This is why your seatbelt buckle gets hotter in your car, even though your seatbelt buckle and the actual cloth seatbelt itself received the same amount of energy throughout the day. Your seatbelt buckle has a lower specific heat and requires less energy. So when they're given the same amount of energy, the seatbelt buckle gets hotter than the seatbelt cloth itself. Water has a very high specific heat, which is why large bodies of water like a lake or the ocean tend to stay cool even in the summer when temperatures outside are very high. Now that we've talked about conduction and radiation, before we move on to convection, we have to understand expansion and contraction. So we're going to take a little detour and talk about them first. As materials cool down or heat up, they're going to lose or gain thermal energy. And as you know, thermal energy is kinetic plus potential, so that's going to affect the kinetic energy of these particles. When particles lose kinetic energy, we know it's going to cause those particles to slow down. If those particles slow down, they bump into each other less often and they take up less space. Think about it like if you had a room full of toddlers, you'd be able to fit a lot more toddlers in that room if you could keep them sitting still, right?
Stack them on top.
But as soon as you start letting them run around, they occupy a lot more space. The same is true of particles. When particles are moving quickly and bumping into each other, they spread out and require more space, whereas when they are moving slowly, they don't bump into each other as much, so the material contracts. Thermal contraction is a decrease in a material's volume that happens when its temperature decreases. When particles gain kinetic energy, then they speed up, collide more often, and as a result take up more space. And we call that thermal expansion, which is an increase in a material's volume when its temperature increases. All objects, all materials, experience some form of thermal expansion and contraction, but it's most notable in gases. It's easiest to see the expansion and contraction in gases. If you've ever taken an inflated balloon outside on a cold day, that balloon will actually start to shrink and shrivel up a little bit because the gas inside is contracting. It's very obvious in gases. It's a little bit less obvious in liquids, and it's even more difficult to see in solids, but it is still happening, even if it's visually difficult for you to tell. Here's some examples of expansion and contraction as you might see them in everyday life. Okay. When you are walking on the sidewalk, you might notice that there are gaps in the sidewalk. This is to prevent cracking. If they made it one long solid sheet of concrete, in the summer when it got hot, it would expand and buckle. What they do is they create these grooves, places where it's easy for cracks to form in a nice straight line so that the sidewalk is still usable even when it expands and contracts. Hot air balloons. When the air inside of a hot air balloon is heated, it expands. So initially that expansion is very obvious. It fills the balloon up with air. But then what also happens is that air, which now has a greater volume but the same mass, is much less dense than the air around it, and then that hot air balloon rises off the ground. And lastly, oven-proof glass. If you just take a random glass cup out of your fridge or out of your cupboard and put it in your oven and heat it up, it will break because glass expands when it's heated and it expands unevenly, so it causes tension, which causes breakage in the glass. Oven-proof glass, like the pans that you have that might be made of glass that are intended to go in the oven, are made out of materials designed to expand less than normal glass does. And as a result, without crazy amounts of expansion, the glass is stable and it doesn't break in your oven. Now that we understand expansion and contraction, we can talk about convection. Convection is the transfer of thermal energy by the movement of particles from one part of a material to another. So we are going to have this happen in a fluid. Okay? Convection, sadly, does not happen in solids. The particles have to be able to move around each other. As a result, it needs to be a liquid or a gas, which in science we refer to generally as a fluid. It happens through the following steps. Matter that's near the bottom of the fluid or near whatever the heat source is for this fluid is heated by the heat source. And then that heated matter undergoes thermal expansion. Thermal expansion increases its volume, which lowers its density. So if you remember, density is equal to mass divided by volume. So if you keep your mass the same, but you increase your volume, you're going to lower your density. So with that lower density, the heated matter rises. While that is happening, near the surface of the fluid, or opposite the heat source where there's no heat source, that portion of the fluid is losing thermal energy to another material, to the air, to the surface it's in contact with, but it's losing thermal energy. When that thermal energy is lost, the cooled matter undergoes thermal contraction. Thermal contraction decreases its volume, which increases its density, and with a greater density, that cooled matter sinks. This sinking and cooling, this Cooling and sinking and then heating and rising continues until all the matter is the same temperature. And then because it's all the same temperature, it'll all have the same density, so there will no longer be any rising, sinking, heating, cooling happening. The alternate rising and sinking of matter that we just talked about is what creates a convection current. A convection current is just the movement of fluids in a cycle because of convection. Convection currents are involved in lots of things you might not even realize are happening around you. For example, the movement of the Earth's oceans is caused by convection currents. So as the large bodies of water are heated and cooled, convection currents form, and those convection currents are part of what causes the actual ocean currents that move water from one location to another. The circulation of air in a room or in your house is also caused by convection. This is why most people put their heaters in their basement, so that when that cool air sinks, it's retaken up by the heater and reheated. The movement of matter and thermal energy that's happening inside the sun is also caused by convection currents, as is the movement of air on the surface of the Earth. So more direct sunlight reaches air near the equator, it's heated to a greater degree. The air near the poles is cooler, so it sinks, and this rising and sinking causes these large air currents, and those air currents drive all the weather on the surface of the Earth. So they're very important. All right, this is where our notes end for today.